All right, first talker today, Chris Paget, and it's Extreme Range RFID. Let's give him a big hand here.
Thank you. Actually, let's see if I can use one of these mics. That's a little better. Can everyone hear me? Can everybody hear me? Yeah. There we go. Okay. All right. A couple of notes about privacy and safety just before I get going here. There is only one type of RFID tag that I'm reading in this demonstration, and that's EPC Generation 2. That's the tags that were handed out at the door. If you have other RFID tags on you and you're worried about them being read, sit on them. Your ass shields them really, really well. The tags that were handed out for the demo, they've all got unique serial numbers on them. So, feel free to assume that I'm tracking every single one of you. Throw them away when the talk's done. Unlike the tags that the federal government issues, you can throw mine away. One quick point about RF safety. There isn't much power coming out of these antennas. There's about 3 watts coming out of this one, and this is receive only. So as long as you're like 2 feet away from it, you're perfectly safe. So don't touch, but yeah. The power amp's not even on yet. You'll see when I turn it on. So okay. So, what is EPC Generation 2? It's electronic product code compared to a universal product code. That's a barcode. EPC is effectively an RFID barcode. It's a 96-bit ID number typically. You can get other size tags. They go from 64-bit up to 128-bit. It's passively powered, so all of the energy that's running those tags and letting them switch on and transmit their IDs, it's coming out of this antenna and out of this power amplifier. So I am powering those tags. Works in the 900 megahertz ISM band, so 902 to 928. There is no security. There is, Barbie doll security, in that they have these kill codes and these lock codes. And if you send the kill code, then the tag will disable itself. If you send the lock code, then the tag will lock itself so that you can't change the ID number. Only problem is both of these codes are sent over the air in plain text with about a watt of RF. So you can just sniff these things off the air from several miles away. It's pathetic, it really is. So no security, no access control. This is the tag that's used in the US passport card. If anyone has one of those, a little card that gets you around North America. Anyone has an enhanced driver's license, it's the same RFID tag in there. It's also the same RFID tag that Walmart used for stock control. They've been using it for pallet level tagging for quite some time, and they're now going to be deploying to every single item. At least that's the plan. So how is this different from traditional RFID? Well, traditional RFID is an inductive system. You have a coil of wire in the reader, you have a coil of wire in the tag, the two couple together with a magnetic field. And each side of that gets to modulate that field and transmit data to the other one. So because it's a magnetic field, we've got an inverse cube law on field strength, which means that the available power drops off as the 6th power of range. So very, very sharp drop off in available power for the tag. Extremely difficult to power these things at long distance. EPC Gen 2, on the other hand, it's much more accurate to think of these tags that you're all holding as radar IFF transponders. So the radar systems that identify friend or foe, that's basically what these things are doing. So you've got a little radio receiver in there that charges up and powers the tag, and then upon being interrogated by the reader, the tag will modulate its coefficient of reflectivity. So you can think of that if there was an aircraft. As the aircraft tips towards the radar tower, exposes more of its wing area and gets a bigger reflection back to the radar tower. As it tips upright, less surface area exposed, less reflection. That's exactly what these tags are doing electronically. So it is radar. It's a proper backscattering system. Inductive coupling, a lot of the time inductive coupling RFID systems are referred to as backscatter. It's not correct. This is a backscatter system. It's radar. And thank you to whoever's attacking my ninja badge right now. So because we're dealing with radar, we're dealing with radio, and we can use radio techniques and radar techniques to increase our read range. We've got proper electromagnetic waves. We've got a transmission coming out here. It's not an inductive thing, it's not a near field, it's proper radio transmission. So we can treat it as radar, and we can use radar techniques to increase the read range. What does that mean? Well, fundamentally it comes down to this, the radar range equation. There's lots and lots and lots of different forms of the radar range equation. Lots of different ways of substituting out different values for different things that you can and can't control. This is the one that I find most useful. It came from ThingMagic, a company that makes RFID readers, so they should probably know a thing or two about how it works. I'm not going to go into this in too much detail, but the two things that I do want to point out is that the maximum range is derived from two things that we can control and a bunch of things that we can't. The two things that we can control are the gain of the antennas. If we put a smaller antenna, if we put a bigger antenna with higher gain, let's say we get 100 times better gain out of our antenna, we should get 10 times the gain out of our read range, because we get the square root of the antenna gain as read range. Likewise, transmit power. If we go up to 100 times the transmit power, we get the square root of that in read range. So going from 1 watt to 100 watts, you'd expect to get 10 times the read range. A bunch of other stuff we can't control, like frequency. Obviously, lambda is a factor in there. And you know, we have some control over that, a little bit within the band, but not really enough to make much difference. So yeah, a bunch of stuff we can control, a bunch of stuff we can't control. One thing that's really convenient with all of this is to work with ratios against a reference. So if we look at a commercial off-the-shelf Gen 2 reader like this, this puts out 1 watt into 6 dBi of antenna and gets about a 30-foot read range. So if we treat that as our reference and then scale everything from there, in theory, if we went from 1 watt to 100 watts, we should go from 30 feet to 300 feet. And we can work it that way in terms of ratios to our reference value. Now, ultimately, that means that we're working in decibels. How many folks are familiar with the basic mechanics of decibels? Okay, most of you. So I'll skip through this then. The quick version is that it's a decibel is a ratio between two numbers. It's 10 times the base 10 logarithm of them. Decibels are really convenient because you get to add them together in order to multiply values. You can also take a square root by halving it. So if you're working in this logarithmic scale, just the number crunching gets quite a lot easier. Obviously, dBs on their own are dimensionless, so they only really express gain. So if we define one of the things that we're defining, if we define one of the points that we have gain in reference to, we get some useful units out of it. dBm and dBi are the two main ones. dBm is how many decibels of power are you putting out relative to 1 milliwatt. So 10 dBm is 10 milliwatts, 20 dBm is 100 milliwatts, and so on. dBi is gain over an isotropic antenna. So an isotropic antenna is one that radiates equally in every direction. Obviously, these Yagis are very high forward gain, they're very directional, so effectively it focuses all of that RF energy into a narrow beam and effectively produces a stronger signal if you're looking into that beam. So we have gain versus an isotropic antenna, and that's where dBi comes from. It's perfectly valid to add these three things together, even though they look like different units, they're really not. If I've got 10 dBm coming out of my transmitter and I put it through a 20 decibel amplifier and into 15 dB of antenna, I've then got, what's that, 20, 30, 45 dBm coming out of the antenna, or 45 dBm relative to an isotropic radiator at least. So you can add these things together and they're not really different units. So the band that we're operating in, 902 to 928 megahertz, ISM band. Industrial, scientific, medical, this is what ISM stands for. And if you're working under these rules, you've got some very tight restrictions. You can only use very low power. 1 watt is, I believe, the limit. You have to make very little utilization, so I think your transmitter can only be on for a maximum 10% duty cycle. You have to hop frequency a couple hundred times a second. Certainly the reader that I've got here hops frequency very, very fast. So it's really tough to comply with ISM rules. But as it turns out, 902 to 928 megahertz is a ham radio band. Ham radio operators don't tend to like it because it's full of all of this ISM crap. There's too much noise. So a lot of ham radio operators will look at it and say, oh, it's not even a ham band because nobody does anything in it. Well, it is a ham band. And in fact, ham radio operators are the primary users of the band. If a ham operator and an ISM operator conflict, it's the ISM operator that has to solve the problem. So by operating under ham radio rules, we get to avoid a lot of the ISM restrictions, and we get to have a little more fun on the way. So let's look at what. So amateur radio licenses, they're pretty easy to get. The URL here is for a training program. You just go up and they'll keep asking you the same questions over and over and over and over and over again until you get them right. And it's the actual questions from the test. So it's no-brainer to pass it. If you actually take the time to figure out things that you don't understand, look them up on Wikipedia, you'll learn a lot out of it. I highly recommend doing it. So once we've done that, we instantly qualify for a 1,500 watt power limit. That's a lot of power. I have an amplifier here that does 600 watts, and this thing scares me so much I haven't even turned it on yet. 1,500 is huge power. The only other restriction specifically for this band is you're only allowed 50 watts if you're within 241 kilometers of White Sands missile testing range. I don't quite know what they're doing at White Sands, but I'm not sure I want to point my Yagis at them and find out. So in general terms, if you're operating under an amateur radio license, you're allowed to transmit an unspecified digital code as long as the specifications of that code are published. So in this case, we've got a digital communication system. There's bits going between the reader and the tag and back and forth. So as long as the URL's there for the standard, you can go look it up, it's all published, means it's fine to transmit at amateur radio power levels. You're not allowed any cryptography. Well, that's not a problem because the tags are so dumb. No limits on antenna, basically as big and bad as you can get, and whatever you're prepared to cart around. The only other real restriction is RF exposure limits. I'm not allowed to fry you guys for some reason I don't quite understand. And then the station has to identify itself every 10 minutes. So you have to Morse code out a call sign every 10 minutes. So let's take a look at a quick look at a commercial Gen 2 reader just to get a benchmark here. So this is a Symbol XR400. This was 250 bucks on eBay. I've talked about this thing before and how it was so cheap because it was broken. It'll do 30-foot read range right out of the box. So you connect it to its standard antenna, all ISM compliant. You'll read these tags from 30 feet away. It's very, very fast frequency hopping. It's so fast that I've yet to find a spectrum analyzer that can keep up with it. You're looking at kind of $100,000 real-time Tektronix gear just to even see the transmission coming out of this. So it's pretty much impossible to just follow the hopping sequence and identify on whatever channel it transmits after the fact, because it jumps around so fast you just can't follow it. As I mentioned, 1 watt of output power, 6 dBi of antenna gain, that's ISM limits. And one of the other things that it does, because it operates in ISM, is it actually checks if you're using an authorized antenna. Supposedly this prevents you from abusing the ISM band. Epic fail. So let's just take a quick look at how we can improve on this one. So the first thing that we can do is replace the antenna. The standard antenna is 6 dBi. These Yagis, they give us 13 dBi, so that's a 7 dB improvement. 50 bucks a piece. So for 100 bucks of antenna, we should get a 3.5 decibel increase in read range. Obviously the square root of our 7 dB antenna gain. 3.5 dB works out to a factor of 2.25, which in this case gives you 67.5 feet. And as I mentioned, we have to defeat the antenna protection first, so let's take a quick look at that. What the antenna protection actually looks like, it's just a 10K resistor from the active element to ground. That's it. That's the sum total of the protections on this thing. When the reader starts up, it looks at each of the read ports, each of the antennas connected, and it looks for the DC impedance. If it doesn't see 10K of DC impedance, it just turns off the port. So it gives us a two-part problem. Firstly, we have to give it that 10K, which is easy enough to do, just solder the resistor inside the reader. Second thing we need to do is slightly tweak our antennas, because if you look at the active element of these Yagis right near the poles here, you can see there's a loop. At DC, that's 0 ohms, effectively 0 ohms. So we need to tweak it a little bit, and you can see on this antenna there's a little filter hanging in line. What that does is, because the filter is, it has a passband over the entire ISM spectrum, so as far as it's concerned, all of the RFID stuff just goes straight through it. But it presents effectively a capacitance to the reader, which is at DC, it's an open circuit. So you combine open circuit with the 10K resistor that we've got inside, and we've bypassed the antenna locks. We've given it its 10K DC impedance. So if you do this and you put it all together, you actually get a read range of 70 feet. So it conforms quite nicely with theory. This is, I believe that in 2005, I think it was, when Flexilis set the RFID record at Defcon, I believe they were using almost an identical reader, almost identical antennas. My guess is that they fried their power amp and that they set their 69 feet by just connecting these antennas to this reader. I'd love to talk to someone from Flexilis and confirm that, but that's my suspicion. Okay, so we can put antennas on. What about amplifying the signal? We want more power. That's where the fun starts. So we could stick a power amp on this and just bump the signal up, but we need to ID, and if we're going to be operating under ham radio rules, we should be a little better behaved. It's very difficult to quantify if you can't see it on a spectrum analyzer. If you don't actually have any test equipment that can see the signal, how do you really mess with it? So yeah, you could just bump up the signal from a commercial reader, but you're going to be breaking FCC rules, and it's kind of ugly. So instead, we go to the USRP, and that's this black box here. This one. So this is, it's a software radio device. Effectively, the computer does all the hard work of modulation and figuring out what that signal needs to look like when it goes out over the radio. Dumps it all over USB. The USRP up-converts it to whatever baseband frequency you specify and just sends it out on the wire. And then likewise in reverse, it comes in, it's digitized, it's down-converted and just dumped over USB, again for the computer to decode it. So very powerful, very flexible, and you can use the one device for a lot of different things. So this top link is for a EPC Gen 2 reader for the USRP. One big advantage that it gives us straight off the bat is its fixed frequency. So we don't have to worry about frequency hopping. We don't have to worry about chasing it after the fact and identifying. We know what frequency it's on. We can control what frequency it's on. The package also includes a Gen 2 sniffer. So I was mentioning that these kill and lock codes you can retrieve remotely. If you have a USRP2 and you download this package, you can just sniff kill and lock codes and anything else that you want. I would recommend, if anyone has a USRP, check out the clock tamer. I do a lot of work with GSM, as you might have heard, and I actually switch back and forth between 64 megahertz and 52 megahertz clocks on the USRP. Clock tamer is by far the best USRP clock I've ever come across. So if you do have a USRP and you do some GSM work, please check it out. So okay, so we've got frequency control now. We know what channel we're on. We've got stability over what frequency we're transmitting at. So we need a way to identify the station. Well, identifying in ham radio terms is really quite simple. It's just a question of Morse coding out a call sign every 10 minutes. Straight carrier wave, no modulation. You can modulate it if you want, but if you want to just treat it as carrier wave, you're perfectly fine doing so. I could have screwed with the USRP implementation and tried to hook Morse code into there, but to be honest, it was too much effort, and there's an easier way to do it. The easier way being having a second transmitter. If you've got a second transmitter that's tuned to exactly the same frequency, then when that second transmitter morses out a call sign, it'll just DOS the RFID signal. So we need a second transmitter, preferably something that we can script easily. So we come to the IME. How many folks have one of these things, or have hacked one of them? Oh, come on, people, you're missing out. So the whole point about these things, Travis Goodspeed put me onto these. They're really quite nifty little devices. Obviously, you've got a keypad and LCD on there. You've got a very, very flexible radio. Reasonable power output, works over a very wide frequency range. C source code available. There's no firmware security. They don't come as standard with SMA and JTAG ports. That was an aftermarket modification. But yeah, if you've got a good FET, you get one of these things for 20 bucks. You've got one of the most flexible radios you'll ever need. So all we need to do is match the frequency and the power level to the USRP. Well, that's easy enough to do with a spectrum analyzer. As it turns out, we need to amplify the signal from the IME just a little bit and attenuate the signal from the USRP quite a bit, mix them together, send them off to the power amp, and we're golden. So quick demo of what that looks like. What I'm going to do here is... Okay, so I've just started the RFID reader. Turning on the power amp. Cover your bits. So what I have here is a little ham radio receiver that's tuned to the frequency that I'm transmitting on. And if I turn the volume up here for a second. So that clicking, each click is a bunch of commands from the reader telling the tags to wake up and activate and do their thing. So on top of that, if I push a button on the IME, you'll hear the IME morse out my call sign, and you should see the screen flash as well. Anyone manage to copy that? Oh, come on, someone must know Morse code. Ah, you're all useless. Anyway, suffice to say, it works. We can identify the station. As long as we've got that thing turned on, it just cranks out a call sign every 8 minutes, and we're legal, so it's all good. Let's turn this power amp off again. Okay, so we've taken care of the identification, and we can now look at just scaling up the power level. So we're ham compliant. We've got an upper ceiling now of 1.5 kilowatts, it's just a question of what we can find now. So this is the power amplifier that I'm currently using. This big box here is actually the power supply for it. This thing will deliver, it's rated at 70 watts, but if you really crank it up, it'll probably deliver 100 before it blows up. Cost me about 400 bucks. Not a tremendously expensive piece of equipment, considering the amount of power that you get out of it. One thing about RF amplifiers, they don't tend to have volume knobs. So you control how much power you get out of it by restricting how much power you put into it. So in order to increase my power level, I've got all kinds of attenuators here, and I just adjust the attenuation before I go into the power amp in order to control how much comes out of it. And as I said, we have to amplify the signal from the IME, attenuate the signal from the USRP, bring it all down to the level that the power amp needs, and off we go. So an interesting artifact about range reads, when the tags turn on, they require an initial burst of power in order to first switch on for the first time. And then once they're operating, they require lower power. So you can actually exploit this to figure out what the current limit is of your RFID read range in this case. If you get your tag, and you have to walk closer to the reader so it gets more power and more power and more power, and then it turns on. But then once it's turned on, you can walk back and walk back and walk back and walk back and walk back, and it turns off. Then at that point, you know that you're limited by power. You're limited by the power that's available to the tag to switch on. So you can amplify your power output. If, on the other hand, you get closer and it just picks up the signal, and you get further away and it just loses it, then that's receiver sensitivity. So just by looking at whether there's any hysteresis on the read range, we can determine whether we're limited by the power coming out of the reader to the tag, or whether the power coming back from the tag to the receiver. It's quite a neat little thing, and it allows us to notch up our output power incrementally, notch up the receive gain incrementally, and just kind of keep track of the whole system. Quite a neat little artifact, quite handy. A few limits on read range. We've got 1500 watts of RF power. Practical antenna limits, obviously, you're not going to be carrying around an antenna the size of a building unless you're really keen. So primary sources of limits on read range. Other ISM stations, obviously anyone else who's transmitting on the same frequency is going to get in the way. Ultimately, the sensitivity of the receiver will play a limiting factor. There's only so small a signal that you can amplify up into something that the USRP can actually make sense out of. Transmitter crosstalk, this is a big one. And this is somewhat unique for this system as well. We've actually got a transmitter and a receiver on exactly the same frequency. In radio, that's actually pretty again, it swamps the signal from the tag and you lose the signal. Other things, ground interference, the antennas aren't completely parallel beam. Some of it will be going down, bouncing off the ground and up at the tag. That scrambles things at the tag. And then when the signal comes off the tag, again, it's going to be bouncing some of it off the ground and back to the reader. So you've got all kinds of multipath effects, all kinds of distortion. Eventually, that's going to be a limit. Atmospheric effects as well. The radar range equation doesn't really work in real life. It's a good approximation, but the atmosphere attenuates things, and that'll get in the way as well. And eventually, when we get up to really insane ranges, the curvature of the Earth is going to be a limit, because we're working with UHF here, and UHF does not bounce off the ionosphere. You can't reflect it around the Earth. So there's a lot of eventual limits that we'll reach. But in the meantime, let's figure out what we should be able to do with this system. Well, we're going from 1 watt of RF power in the commercial reader to 70 watts coming out of the power amplifier. That's an 18 decibel increase in power, which from the radar range equation, you get the square root of that as a range gain. We should see a 9 decibel increase in range. From the antennas, we've gone from 6 decibels to 13 decibels over isotropic. So 7 dB increase gives us a 3.5 dB range increase. So overall, we should see a 12.5 decibel increase in range. So comparing that to our 30 feet reference from the commercial reader, we should see a range of about 565 feet. What did we get? 217. Not what I was hoping for, but if you can see in the picture, my wife in the distant background holding the tag, 217 feet is a long way to be reading an RFID tag from. So what happened? Why so little? Why didn't we get the full 565 feet? Well, as it turns out, that was with about 3 watts of RF power as measured on my meter. The meter wasn't entirely accurate, so it's realistically more like about 10 watts. Increasing the power beyond that actually decreased the read range, which is kind of counterintuitive until you look at the picture. This was, I was using an empty lot by the Googleplex in Mountain View. As it turned out, not so empty at the end of it, but anyway. In the background, you can see the tent and the chain link fence. That's Shoreline Amphitheater. And that's a 10-foot high steel chain link fence that runs all the way around it. As I was increasing my power to power the tags at higher distances, I was getting more and more reflection from that chain link fence. Clutter. So as I increased my output power, the signal coming back off that chain link fence increased and just swamped the tag. So clutter was the limit. However, if you work out the numbers on it and you do the number crunching, 10 watts of RF gives us 10 times the power, so 10 dB power gain. 7 dB from the antennas. If you work it out, we're actually still consistent with the radar range equation. So we can swap out antennas and see a square root of the antenna gain from the radar range equation. If we increase power, again, we validated the radar range equation. So yeah, okay, we got 217 feet, but more importantly, we validated that these tags, the read range is dictated by the radar range equation. So if you actually, do the math, it should still be able to do that. I'm trying to get access to, all kinds of different places that would be nice wide open areas to test in. If anyone has any friends at NASA Ames that wants to, give me access to a runway for a day, I'll be your friend forever. We did actually get roof access. We not quite roof access. We got access to DT suite, and we fired off the roof, off the balcony. As it turns out, 120-degree air isn't really good for power amps that get really, really hot anyway. Magic smoke did escape. I was up quite late last night fixing all of this, so I'm fingers crossed that something works. Okay, so demo of actually reading tags then. So just to give you an idea of what kind of range I'm looking at. So unfortunately, one of the problems with the Gen 2 RFID reader on the USRP, it needs an extremely low latency USB. The Gen 2 is very, very sensitive to latency. So if you've got a full operating system, it's too much. It's going to get in the way. So I've got a very, very bare bones Debian installation here running the absolute minimum possible, so there's nothing that gets in the way. Unfortunately, that means that it's pretty much incapable of talking to the projectors here. So hopefully what we're going to try is, I believe there was a plan to focus video on the screen and try and project that. So we'll see if that works. Let me just set this up here. So. And if you can actually see that. Hey, too far. Okay. So what you're looking at, there's three things that you're going to be seeing on the screen here. White text is where the system has interacted with a tag in some fashion. Maybe hasn't, quite gotten the response it expected, but it sent a command and it got a response, something went on. If you see a red text means that it's read a tag, but something went wrong. There was an error, maybe the EPC that came back failed its checksum, something like that. Blue text is a successful read. So don't worry too much about what's actually on the screen, just look at the color of the text. White means it's interacting, red means it's a bad read or fault of some kind, blue means it's a successful read. So let me turn the power amp on here. Okay, and straight away, without anyone holding up any real tags, you can see we've got collisions. So that's largely due to the sheer density of tags in this environment. It's really not designed for this many tags. So we'll see how this copes. If you look at the tags that you were given, you should see there's a metal strip inside it. The orientation of the metal strip has to match the antennas. It has to be the same polarity. So make sure to hold the tags up sideways so that metal strip is vertical, just like the bars on the antenna. So you can see there's quite a huge amount of traffic scrolling by here. If I could ask maybe the first 5 rows to put down their tags, that was a lot more than 5. But okay, so you can see, we're getting back to, just in front of the camera area, maybe another 5 rows back. Okay, the ID me is identifying at the moment. No, let me just restart it. Did I mention that it's kind of flaky too? So, okay, so we're now interacting with tags, well behind the cameraman here. I can't actually see whether there's any successful reads. Are we getting any blue reads here, or not? Okay, so it's clearly interacting with tags. I was kind of hopeful that we'd get some successful reads, but like I say, all the Defcon badges and your sunglasses and even your faces are causing clutter. So not too surprised it doesn't work. What I am going to be doing though is once I get back to California, I'm actually going to be calling the folks from Guinness World Records. And once I get to access to a test range, I'm going to get them down because the 217 feet that I read at, I believe that is a world record. So I'm going to get Guinness in, get it certified, and then announce it officially. Okay, so let me turn the power amp off. I am also, after the talk, I'm going to be up in the hardware hacking village. So if you want to see the equipment up close and have a play with it and just validate that it does read tags in slightly less hostile environments, please feel free to do so. Okay, so what's the upper limit here? We've clearly validated the radar range equation. We've got solid evidence that the radar range equation is valid in this environment. So how far can we take it? Well, under ham radio rules, we can have 1.5 kilowatts of transmit power. So what's the biggest antenna that we can get? Well, this is the largest I've been able to find. This is a 2x2 array of 26-foot long Yagis. So each Yagi, each boom is 26 feet long, and the 4 antennas that you see actually are all configured as one big antenna. So we actually get about 26 dBi gain out of this. And if you run the numbers, if you put a legal limit transmitter into that big an antenna, you should get a read range of about 2 miles. So that's what you can do with ham radio. What about the military? This is a naval radar system called ANSPS-49. SPIS-49 is how they refer to it. Runs at 851 to 942 megahertz, so nicely overlaps our band. 280,000 watts peak power. That's shiny. Want. Dish 24 feet wide, 14 feet high, gives us about 35 dBi. If you crunch the numbers on this, assuming it's possible to backport a Gen 2 system into this, you should get a read range of about 80 miles. Kind of scary, but we're not done yet. Logical limit. Arecibo Radio Observatory. Believe it or not, amateur radio operators do get access to Arecibo sometimes. A couple of months ago, there was a group got access. They put a 400-watt transmitter on the Arecibo dish, pointed it at the moon. And the idea was that you had amateur radio operators all around the world with little tiny handheld Yagis, much smaller than this, pointing them at the moon and bouncing reflections off the moon to Arecibo and talking from anywhere around the world to Arecibo with a moon bounce. It's kind of neat. Entirely amateur run. So it does happen. It's theoretically possible that we could put a 1.5 kilowatt legal limit transmitter on the Arecibo Radio Observatory. Again, if you crunch the numbers with that, 317 miles. To put that into perspective, if you were to put an EPC Gen 2 tag on the International Space Station, you should be able to read it with this as it flies overhead. It's ridiculous range, absolutely preposterous, just insane. So let's bring it back to reality here. 317 miles, it's probably not going to work. You're going to get a lot out of it, but 317, maybe that's arguing a little much. Either way, we have still validated the radar range equation in this situation, so significant ranges are definitely possible. I've done 217 feet. I believe the equipment's capable of 500, maybe more, and clearly we've got a problem here. We can read these tags at very, very long ranges. Eventually, round trip time is going to become a limit. It's very sensitive to timing. Either way, I firmly believe that it's possible to read these things at over a mile. And I hope to prove that, but for the moment, I'll settle for the little Guinness certificate, assuming they come through with that. In the meantime, clutter is the primary limiting factor. Certainly the ranges that you can get from the available power and the available antennas, clutter is going to be the most significant factor. So I had a bunch of scenarios here for long-range RFID. I gave this talk at Black Hat, and they give you a little more time at Black Hat. So I'm just going to kind of skip through these and give you my top 3 threats for this. So assuming that you can read RFID tags like these from 200 feet, and assuming that they're in identity documents and Walmart and all the rest of it, in other words, assuming nothing beyond what's actually real at this time now. Assuming an attacker gets hold of this stuff, what can he do? I'm going to skip through most of them. These slides are already up on my blog. If you've seen my Twitter, There's a link from there to my blog, and all the slides are up there. So I'll skip these. There we go. Number 3. So I bought 1,500 RFID tags to give away at Black Hat and Defcon for $100. These tags are reprogrammable. You can give them any ID number you like, which means that you know that the way that the numbers are allocated, let's say New York State wants to issue a bunch of enhanced driver's licenses. They go to EPC and they say, give us a prefix. It's like a MAC address, you can think of the way that they're structured. So you can look at that prefix and you can know where that tag came from. So if you kind of flip that on its head and you take those 1,500 tags and you reprogram them with a known prefix and then sequential numbers after that, you can, produce 1,500 effectively passport cards or EDLs or whatever kind of tag it is you want. Wait until your friend crosses a border, drop that in his trunk or stick him to his car. I don't know what the hell Customs and Border Protection are going to do when they see you try and cross a border with 1,500 passports in your trunk, but it ain't going to be pretty. I'll say the same thing I did at Black Hat. Please don't do this, or if you do, record video and send it to me. Sniffing clothing. This one creeps me out. I don't like this at all. Walmart have stated that they're going to be using this technology to identify individual SKUs. So you'll have distinct RFID tag numbers for every size, every color, every style of every item of clothing in that store. So when you combine that with the ability to read tags from a mile away, 10 miles away, however far away, I can stand here on stage and know what kind of underwear you're all wearing. That gets creepy really quickly. I don't really want to think about how that can be abused, but just the concept of knowing that much detail about someone from that far away, it's just not right. And the number 1 that I came out with, and the reason this gets my number 1 is because I believe it's a viable business model. You can actually install multiple RFID readers at the doors to a mall, read people's credit cards, read their driver's licenses, every single tag that walks through, correlated all together by time because you've got these very short-range reads, and then track those identities from the long-range tags that they have on them. So you can watch people as they wander around the mall, you can see what route they take, you can see whether they stop in any shops, you can see whether they pause and look in any windows. You can get a huge amount of information about how people behave within that mall environment. And to a typical mall owner, that's going to be very valuable info, because they can then use that to figure out, well, most people could take this way around, so we'll charge more for this advertising spot that's in the more popular path. All this kind of stuff. It's all the kind of really deep data that folks that run malls really love. And again, it's in the majority of states, it's perfectly legal. Most states do not have any laws on RFID sniffing, so you can do this. It's not a problem. And like I say, it's probably a viable business model as well. If someone wants to, you could make some money out of it. So 2 quick defenses, just before I stop for some questions. 2 solutions for all of this. And I'm sure that pretty much any privacy advocate would agree with these 2. Number 1, do not put RFID in identity documents. Here's the thing about the tags that you were given. Those all have unique serial numbers. But you don't know whether I arranged with the people at the doors handing out the tags. Let's say I knew that a certain person was coming and I wanted to make sure that that person got a specific ID number. You don't know if I was doing that. You don't know if the people at the doors had hidden cameras and they were taking pictures of everyone and making a note of what RFID tag corresponds to what face. You don't know how those tags could be abused by me or by anyone else. But here's the thing. The tag that's in your driver's license, you can't throw that away. These ones you can. That's the big difference. So all of the privacy threats are exactly the same, but when it's in a federally issued identity document, you cannot escape it. Secondly, disable all store issue RFID tags upon purchase. A lot of stores that use RFID do this, but because of weaknesses in EPC Gen 2, you can either kill the killers or reprogram the tags to change the lock codes. There's all kinds of ways of preventing people from disabling these tags, and there should be some kind of consequences if that process failed. Beyond that, informing people that RFID is in use is always good. There's a lot of FUD surrounding RFID. A lot of people use RFID and don't really want to call it RFID because RFID has such a stigma. Either way, if you're worried about an RFID tag, stick it in the microwave for 3 seconds. 3 seconds in the microwave will kill pretty much any RFID tag that you'll ever come across. Be careful though, because 5 seconds in a microwave will probably set fire to any RFID tag you'll ever come across. And then also bear in mind, if you're doing this to an identity document, technically you're tampering with your ID, so depending on what kind of ID and what people want to take a look at out of it, you could be done for a felony at the end of it. So I guess I've got a few minutes for questions. Yes?
Are all of the RFID tags in that same radio band? Different generated tags?
So the question is, are all RFID tags in that same band? Well, all EPC Gen 2 are in that band, but there's lots of different bands to use for RFID. Lots and lots. Yes?
Have you ever seen any
Have I seen people sniff 13.56? Yes. 13.56, there is actually an upper limit in terms of how big you can make the antenna and how far you can project a magnetic field from it. I think that limit lies somewhere around 70 feet, and it's pretty... that's the passport book, yes. Another question? Say again? These ones? Why not? It's fun. Okay, so I think that's about it. There's Q&A in a room out here afterwards. Thank you very much.